I am extremely pleased to welcome and introduce Dr. Daniel Swain to members of the Ecologically Sound Practices Group, the Marin Wildfire Prevention Authority, Fire Safe Marin, and Fire Safe Leaders, Marin Master Gardeners, environmental leaders, and other members of the public, including the Mayor of Ross. Thank you for attending. Thanks everyone for being here, and enormous thanks to Dr. Swain for sharing his time and expertise with us, and to Bell for organizing this important event today. Dr. Swain grew up in Marin, graduating from San Rafael High School. He attended UC Davis, receiving a Bachelor of Science in Atmospheric Science with the highest honors in 2011. Only 6 years later, Dr. Swain earned a PhD in Earth System Science from Stanford University. Since 2017, Dr. Swain has received multiple honors and hundreds of thousands of dollars in grants and has published nearly 40 articles. Most of you already know Dr. Swain as the author of Weather West blog, which provides real-time perspectives on California weather and climate. You've probably also read Dr. Swain's quotes as he engages extensively with journalists and other partners to facilitate broadly accessible, scientifically informed media coverage surrounding climate change, serving as a climate and weather science liaison to print, radio, television, and web media outlets. If you don't already, you can follow Dr. Swain on Twitter at WeatherWest. I guess it's called X now, on X at WeatherWest, and you can find him on YouTube. Currently, Dr. Swain holds joint appointments as a climate scientist within UCLA's Institute of the Environment and Sustainability, and as a research fellow in the Capacity Center for Climate and Weather Extremes at the National Center for Atmospheric Research in Boulder, Colorado. And he is also the California Climate Fellow at the Nature Conservancy. Bell.
Yes, I'd like to say a few words about his research in science. He studies the dynamics and impacts of Earth's changing climate system. He's especially interested in how climate change is affecting regional weather and weather adjacent extremes, including the nuanced spatial, temporal, and intensity characteristic of events like droughts, floods, and wildfires. But his recent work has focused primarily on two parallel but related tracks. First, he has sought to understand shifting regional hydroclimates, including the processes driving and impacts resulting from amplification of severe droughts and mega floods in a warming climate. And collectively, this line of research seeks to answer the question, how will hydroclimate and volatility change in a warming world? And second, he's embarked on multiple collaborative research projects focused on understanding the climate-related factors behind increasingly severe and destructive wildfires that we are seeing across the American West, as well as how climate change might affect efforts to mitigate the escalating wildfire crisis. A collective aim of both these research tracks is to develop empirically supported hazard mitigation that benefit both society and the environment in an era of increasing climate extremes. And the other person who's going to be talking today to us on the subject is Mark Brown, who is sitting here. Mark is the executive officer of the Marin MWPA, and most of you know Mark. Maybe you don't know much about him other than the work that he's doing now, but he started his career as a volunteer firefighter in 1986 in Sonoma County, and he was hired by the Marin County Fire Department as a firefighter paramedic in 1991, and he retired as a deputy fire chief after serving for nearly 30 years with Marin County Fire. He retired in order to assume the position of this job here as the executive officer. That was in September 12th, 2020. And currently, he now confronts and finds solutions for climate change, and has been very busy in seeing how what's happening in his work is influencing climate. So Passing it on to you, Mark.
Thank you, Bill. And I know you guys all came here to see Daniel Swain, so I'm going to be as brief as possible. Just some logistics for you. We do have water and snacks in the back. If you need some water, you want some snacks, if you need to go to the restroom, out the door, either way, if you go left or right, you'll be able to find restrooms. And then due to the volume of people that we have both online and in person, rather than passing a mic around for question and answers, we will have Ted Briggs passing around 3x5 cards. If you want to ask any questions, you can write them on the 3x5 cards. For those of you who are online, we have the Q&A feature enabled. Put in a question on Q&A. We will put those same questions on a 3x5 card. Our goal is to collate those questions and put them in categories. So not every question might be individually answered, but that category, we will answer that question. And what I feel I can bring to this conversation is, well, first of all, I had a couple of months ago, Daniel and I had a phone call for about 30 minutes, and it was an amazing phone call, in my opinion, from what I was able to learn from him. Any good wildland firefighter wants to be somewhat of a meteorologist because it drives so much of what we do on the fire ground. So being able to talk meteorology and climate impacts with Daniel was incredible. And so what I hope to be able to do today is if Daniel starts pulling on a string that I think is really interesting when it comes to meteorology or the climate impacts, I may prompt him certain directions. But I'm also going to probably interject a few times and how climate impacts have represented themselves on the wildland fire ground in my observations. I went to my very first wildland fire in 1986. My first big one was in 1987 in the Mendocino National Forest. All the way through 2020, I was going to fires, and I definitely saw the change in fire behavior from when I started in 1986 to what we are seeing now in 2024. So there's going to be some examples that Daniel gives that he talks about the science behind it, and I'll be able to talk about how that's impacted the wildfire behavior and or how that's impacting the work that we are doing before a fire ignites. And with no further ado, I'm going to pass it off to Daniel and we'll put up the slide deck.
All right. Well, thank you for those introductions, and thanks for the invitation to be here today. As you heard, I did grow up in Marin County. I spent a lot of time mountain biking on Mount Tam some years ago. These days, I do live in Boulder, Colorado, another place at very high risk of wildfire and where there have been some recent catastrophic events. I even have a few photos and a little bit of footage from those events that are, to me, local, but there's actually some lessons there that are parallel with Marin County, even though the climates are actually very different between these places. So I'll reflect on that a little bit. Then I'm going to start out with some climate and climate science in California 101, and then you'll transition from talking about the atmosphere to fires directly about halfway through. And as you heard, there might be some constructive interruptions, so we can talk about, have some sidebars on some of the more interesting pieces here. Should I move this over or? Okay.
It's your choice. If you want it next to you, go for it.
Let's see. I think all right. So as I mentioned, California's climate is a little bit weird in the context of the US and North America. We're so used to having all of our water fall during the cool season. It turns out that's actually not the way it works most places. Usually the warm season is also the wet season. It's in these so-called Mediterranean climate zones around the world where that's not the case. California is one of them, although the funny thing is even the Mediterranean actually gets more summer rainfall than coastal California does. It's one of the driest places in the world during the dry season. The reason I mention this is it means that our dry season, our fire season, aligns with the hot time of year. There are a lot of places in the world where fire season is in the transition seasons or even in winter when it's cold and dry. Not so in California. We get the dry and the hot all at the same time. And the reason for that is that the state exists sort of at this climatological boundary zone. And it's not a fixed boundary. It's roughly a latitudinal boundary between the more stable, dry subtropics to the south and the more active, moister, cooler mid-latitude regime to the north. But that's a dynamic partition. It shifts seasonally, which you can see in this animation here. It's dry in the summer and wet in the winter. And there is a progression as this wet pattern sort of starts in far northern California and sweeps southward through the late autumn and the winter months typically, and then before retracting back northward again in the spring. That gives us, of course, a strong seasonal cycle as the storm track and the jet stream does this poleward shift seasonally. But it also shifts season to season. So we often hear about El Nino and La Nina, and why they matter is because they tend to modulate where that latitude of the boundary is from year to year. In El Nino, it's further south, higher likelihood of some wetter conditions, and the reverse is true in La Nina. So we have this, we're sort of in this boundary. Sometimes it bisects California right around the latitude of the Bay Area and Marin County. And so sometimes that makes seasonal predictions tricky. But what it really means is that we have a lot of variability. Season to season, we have a drought every year. It's called summer in California, which in most parts of the world would be an astonishingly dry 3 or 4 month period, but here it's just normal. We also have a lot of year-to-year variability. We have exceptionally wet years. We've seen a couple of them recently, and also exceptionally dry years. And we've also seen more than a couple of those recently. In fact, we've seen quite a bit of both in the past 10 to 15 years, which is one of the main points I want to get to later. And so in the context of the US, certainly, and really in a global context as well, outside of some other Mediterranean climate zones, this amount of year-to-year and season-to-season variability is almost unique and predisposes California to both a high likelihood of drought and flood. We spend more time in the extreme states than in the middle in this part of the world, relative to a lot of other places. And I'll sort of cut to the chase here in terms of what we think California's precipitation future looks like. When it comes to average precipitation, I am going to tell you that we don't really have much of an idea of how it might change. It genuinely might increase or decrease. But what we know is that the extremes will become, well, more extreme. So drier dries and wetter wets. And it's a little bit counterintuitive how that might be the case if we don't know what's going to happen on average. But I'll get into that a little bit more in a minute. And so the reason I bring this up first is to drive the main point home right at the beginning, but also because sometimes folks will focus on those projected mean trends. You look at climate model data, some of these synthesis reports, they'll show little statistical agreement and small magnitude of mean precipitation change in California, which, if that's the only variable we look at, I think we're likely to be missing the point, essentially, when it comes to the changes that are consequential for both, well, flood risk on the one hand, although that's not the top focus of today, and drought and fire risk on the other. And so in this setting, as I mentioned, we already have in California a strongly seasonal cycle, dry summer, wet winter, with some degree of transition in between. Those transitions themselves vary a lot from year to year. Some autumns are really dry and we have a lot of fire activity. Some autumns are actually pretty wet and there's not much fire activity at all. Spring is more consistently low fire activity because we always get some moisture in the winter. But even there are some springs are quite dry and warm and others are a lot wetter and cooler. And the last couple of years in California, we've had wet winters and pretty mild springs as well, which is quite different from what a lot of the 2010s look like.
I do have a question on this one for you, and that is with wetter winters, but perhaps a smaller period where it's wet. What do you think, especially in, let's take away the snowpack of the Sierras and let's focus on Marin. Do you think the volume of rain that we have is more important, or do you think the time period that the rain is coming is more important in setting us up for what type of fire season we're going to have?
Yeah, this is a good question because I think it really is both, depending on which aspect we're talking about. Clearly, if it's the length of fire season, the period during which it's dry, the number of dry days, if you get the same amount of water, but you get it on 5 days in winter and every other day of the year is dry, obviously you have a much longer fire season and higher flood risk too. But the volume of water matters in terms of what the vegetation does also. And I'll talk about this in a minute, but there is this notion that in some ways the worst climate for wildfire is not one that gets perpetually drier, because at a certain, you have this initial pulse of fires in that case, and then they start to attenuate when you sort of start to lose things to burn. That is not what the future likely looks like in California. Instead, it's these increasingly wide swings between really wet conditions when we do get all this abundant fine fuel, grass and brush, herbaceous vegetation growth, as we have these past 2 seasons, and then we dry the heck out of it in the subsequent periods that are really exceptionally record-breaking hot or dry. So I think that in general, and this is sort of what I'm alluding to here, you can kind of see the fact that if the winters get slightly wetter and the fall and spring gets slightly drier, okay, that sort of evens out to little annual change, but it doesn't really even out in terms of impacts. It means all 3 seasons look pretty different than they used to. And the average is more or less a statistical construct that doesn't matter much for practical purposes. So drier autumns in particular, I think, are a real risk from a wildfire perspective. Because drier springs, yes, it means you have a longer dry season. It means you have more months of drying. But I think it's unlikely that even in the future we'll see really high fire risk in spring in most of California. That would be kind of maybe during an exceptionally severe drought. But otherwise, I think the spring is likely always to be the time of year where everybody can really take a breather. But those drier autumns are going to be a real issue for a couple of reasons. And one is that, of course, autumn follows summer, and summer is the warm season when we know it hasn't rained. And when vegetation is at its driest, it's also when in northern and southern California, we tend to get those offshore winds. So we get those autumnal heat waves at the same time of year when we're most likely to see offshore winds, so warm, dry winds from land to sea, and when the vegetation is at its peak seasonal dryness. And so it's precisely when the vegetation is most flammable that we're most likely to see the wind events that put us in the upper end of the fire weather distribution. So I'll talk about that a little bit more. But that's one way that the seasonal shift in autumn, if this ends up being correct, which we think it will be, it's a prediction. So far it has happened. We are seeing drier autumns on average in California. But if that persists, it means that there's going to be more overlap between dry vegetation season and offshore wind season. And that in Marin in particular, I think is where some of the highest risks exist. It's these late season events rather than sort of the mid-season events. You can get fires, of course, whenever it's hot and dry, but it's those late season events where you have that really potentially upper end combination of dryness and strong winds. So I think I covered most of these points. We can cross off snowpack and Marin since, for better or for worse, there never been much snowpack unless you're talking about the occasional top of Mount Tam dustings. But this is an issue for ecosystems, of course, because it means that whatever you have is adapted to a dry season of a particular length with a particular amount of variance around that length over time. If it may be that some of these ecosystems can handle 1 year outside of that range because occasionally that would happen naturally. But what happens when every year, if you have an extra 30, 50, 60 days that are dry? That's a pretty significant shift. If every year you have an extra month or 2 of dryness, the vegetation somehow has to compensate for an entire extra 2 months that you're not getting water delivery. It's one thing if you can water or irrigate your yard, but you can't irrigate the landscape at scale. And so that becomes a significant consideration in terms of the length of the growing season agriculturally, or in terms of the natural vegetation, and also the length that plants in natural ecosystems have to deal with not having an input of water. And just to illustrate, this probably is fairly obvious to folks, but this is just one example from Southern California about what happens when we do get these sorts of whiplash events. And this is a slide I created in early 2018, and so much has happened since 2018, and yet this example is still fairly dramatic, and so I've kept it. The photos are of the Thomas Fire on the left. This was burned in Ventura and Santa Barbara counties in December of 2017, at the time becoming the largest wildfire in modern state history, causing a lot of destruction, and was immediately followed within just a matter of weeks by a catastrophic debris flow downstream of the fire zone that killed quite a few people and destroyed a lot of buildings in Montecito in Santa Barbara County. I went up there shortly after this event, and you could still smell the pulverized rock in the air a couple weeks afterward. And, this is just an example of how, if we look at the average climatologically over that period, it was mostly sunny and breezy on almost all of the days during that period, with below average precipitation that, of course, doesn't characterize any of the important things that happened in Santa Barbara and Ventura counties during that period. So just reemphasizing that if we only look at the average trend in temperature, the average trend in precipitation, we're going to completely miss almost everything that matters from the context of specific hazards and mitigating the risks of those hazards.
And this is going to be one of the spots where I was going to show where climate change intersected with wildfire. And I was assigned to an incident management team that was assigned to the Thomas Fire. And I was the operations section chief that created the plan to suppress that fire. December 5th or 8th, it started. And It was not warm. And when we always relate heat to wildfire threat. Well, heat really is not that much of an indicator towards wildfire threat, except as Daniel's going to talk about, heat increases how much moisture the air can hold. Therefore, it changes humidity. That to me is the biggest driver of what heat does. We actually had one moment where we had sub-zero temperatures and still had red flag fire conditions. We had 17 red flag days on that fire, 15 of them in a row. And at the time that this fire occurred, it was 11 months of no measurable precipitation on the fire footprint. So that set up for explosive fire conditions. And what the problem we have with those explosive fire conditions, it's total consumption of the fuels and what it does to the soil. And it makes the soil more likely to move if there is a precipitation event. If we have a nice low intensity fire, then the roots and the vegetation can stay in the ground. The soil chemistry doesn't change, and the soil has a better chance of not moving if there's a large rain event. So we were so worried about the soil conditions that we brought in, I forget what WERT stands for. Do you remember what WERT stands for? A team that goes out and evaluates the soil and says, this is the probability of landslides. And so obviously the report came back that there's going to be tremendous potential for movement of soil. So fortunately, it didn't help the people in the impact area in Montecito, but there was a high indication that was going to occur. And when the weather event came, the fire service in California pre-positioned hundreds of resources down towards Montecito to be ready for the mudslide that did happen that unfortunately killed a lot of people. But it's not just the back and forth, but it's also the intensity that the fires are burning at that makes the soil so much more unstable.
Yeah, that's right. And in this context, Southern California, the transverse ranges in Southern California are particularly susceptible to these kinds of debris flows, which are kind of a hybrid event between a flash flood and a mudslide. It's a very high velocity, very high water content, like slurry, essentially, that comes down with real force down the mountains. And the mountains there are very steep. The problem in this case and in many post-fire environments is as you mentioned, we lose a lot of the vegetation that might slow down runoff. You can also develop what's known as a hydrophobic layer on the soil, so literally a water repellent layer on the surface. It's almost like pavement in terms of how much water ends up. I've actually done this with a water bottle in a place that burned just a couple of weeks previously, and it just beads off. It does not soak into the underlying soil at all. And then in this case, what happens is it also provides material that can be incorporated into the flow. So all the ash, there was a large amount of ash. A lot of vegetation was transformed into this powdery ash on the surface, and that actually becomes part of this concrete-like flow. You can sort of see it in the lower image there. That's literally what it looked like. So there's sort of good news, bad news here in Marin County context. We don't live in the transverse ranges. The debris flow risk is considerably lower because the geology and the geography is different up in Marin County. But I do think that, in this context, the debris flow risk may be lower, but, Marin County is at a high risk of landslides and mudslides to begin with. So if there are large fires on steeper slopes, we're going to see that risk. And also there's just the more ordinary flash flood risk. The more area of a watershed you burn for some years thereafter, a given amount of rain will produce a larger increase in the runoff and in the creek and stream flows downstream. So imagining, some of the creeks in central Marin where we've had flood issues over the past couple of decades, if you had a big fire in the Mount Tam watershed, for example, even if it didn't result at the time, in significant losses from the fire directly, there could be pretty significant risk the next winter and the winter after from increased flash flood risk on the creeks in central Marin. That would be a very plausible outcome, just to sort of tie it to Marin specifically. So this is an issue throughout the West. Fire and flood, we see a lot of both, different seasons in different places, but the risk is one I think that we're going to be thinking about quite a bit in the years to come. And we've already been talking about these, so I won't belabor the point, but these are just images of the same part of Northern California up in Butte County, Lake Oroville Dam, not far from where the Camp Fire burned in 2018 that destroyed Paradise. It was either 2018, I think it was 2018. And we just see these back and forth images. This is less than a decade of snapshots of the same dam going from extremely dry conditions to so wet that it almost blew out the dam to completely empty again and then completely full again. And I could have added another image from last week of the actual dam surface having burned in a fire last week up in Oroville. So I mean, there's just this incredible sequence of events that's really encapsulated by what's happened in Butte County, which has been hit extremely hard just by this succession of fire, flood, fire, flood, fire, fire, fire in recent years. Marin has been a bit luckier in that regard. So we'll talk about that. Quick climate change 101, the changing character of precipitation in a warming world. And I don't want to get too technical or focus too much on the details, but I want people to squint a little bit at these essentially deliberately and note that the left map looks kind of different from the right. This is sort of where the blues and greens are places where precipitation might increase in a warming climate, and the browns are where it might decrease. But the difference between mean and extreme precipitation is notable. With mean precipitation, there's a lot of regions that are kind of not really bright color in either direction, where there's not a lot of confidence. If I zoom in, I'm going to do that. These are the zoomed in versions on California. If you look at the mean, it doesn't look like much is changing. But then look at the zoomed in version of the precipitation extremes, and you can see that it's a completely different picture. And there are lots of places on Earth where the mean precipitation change is either small or genuinely uncertain scientifically. But even in those places, there's almost unanimity from the scientific evidence that we will see a large increase in the most extreme precipitation events. So how can that be? That's partly because the global mean precipitation increases by a couple of percent per degree, although your mileage may vary depending on where you are. But extreme precipitation magnitude increases by something like 5 or 10% per degree centigrade of warming. That's a much, much bigger number. So how does that work? First, I got to talk about evaporation, because that's the other side of the coin when it comes to, especially when it comes to water scarcity and drought and wildfire. Climate scientists will often say something like relative humidity won't change a lot on average. But again, if you take one thing away from this talk, it's go beyond the average. That's not true over land, it turns out, where in most places it's likely to decrease, especially across the Amazon, but also across the interior of the American West. But even if relative humidity did absolutely nothing on average, even if it stayed exactly the same, we would still be dealing with changes in a different kind of humidity known as the vapor pressure deficit. Really, colloquially, it's the thirstiness of the atmosphere. What is the propensity of the air around you to draw moisture out of things mainly being plants and soil in this context, bodies of water as well? What is the evaporative demand of the atmosphere? It turns out that increases exponentially with temperature, even if relative humidity stays the same. And so even if we totally ignore changes in relative humidity on average, we still have to deal with the fact that the atmosphere is getting thirstier and thirstier and thirstier and demanding more and more water out of the landscape and out of plants, importantly. And this is something I like to call the expanding atmospheric sponge effect. I'm trying to actually get this through peer review. I'm not a very good visual artist, so I had to create an image that wasn't copyrighted for this paper, but maybe coming to a scientific journal near you soon. But the basic idea is this: the atmosphere does act like an increasingly large sponge as temperatures increase. In fact, after temperatures increase locally by around 3 degrees centigrade, that's a little over 5 degrees Fahrenheit, so not a huge amount, you have a sponge that's effectively 23% larger than it used to be. That's a pretty big difference. And the reason the sponge analogy works, for anybody who has a background in physical chemistry, this is essentially a tangible consequence of the Clausius-Clapeyron relation, which states that the saturation vapor pressure over the surface of a fluid, essentially where there's an infinite amount of the fluid to potentially evaporate, increases exponentially with temperature. Well, in this case, on Earth, water is the relevant fluid, and we're warming the climate quite a bit. But what this means in practical terms is that it increases the ceiling both on precipitation intensity, but also on evaporation intensity, evaporation demand, which is sort of what I'm talking about here. And in practice, this means, as I mentioned, the atmosphere becomes both thirstier when it's not raining, which in California is much of the year, but also capable of much heavier downpours when it does rain, which again in California is essentially a wintertime phenomena, although that's not true everywhere. And all of this is something that we're terming hydroclimate whiplash, this idea that we swing back and forth between progressively drier and wetter extremes with either greater amplitude or greater frequency than we used to. All while in some places precipitation on average may not change. And so this is the signature, I think, of climate change. This map, again, don't worry too much about the details, but the point is almost all of the map, and it actually looks a little bit washed out on the big screens, but I assure you, there's purple almost everywhere but the middle of the Atlantic Ocean, where there aren't too many people on a permanent basis. There's an increase we expect in this in this broader hydroclimate whiplash, essentially everywhere, especially over all land areas, which is where people tend to live. And also, if you look at the bottom plot, my point is if you plot how much this might change as a function of the warming itself. So this is not time on the x-axis, but degrees of potential warming. We don't know exactly how far we're going to go, but we hear about these warming targets of 1.5, 2 degrees centigrade of global mean warming. What we see is that there's an acceleration of these risks between about 1 and 3 degrees of warming, which is smack dab where we are right now. We can quibble about the exact amount of warming that we've seen, but it's somewhere between 1.3 and 1.5 right now on a global basis. And so, this is going to be a signature, not just in California, not just in the West, but more broadly around the world. And so this is something that's of relevance for really all fire-prone regions and some regions that were not necessarily historically fire-prone. So I want to focus more now on wildfire itself. And this notion that I think there's pretty broad agreement that there is an escalating wildfire crisis. There's a lot of disagreement as to, at least colloquially and in different circles, as to what the most important factors are. And that's partly because there genuinely are multiple factors. It isn't just any one thing or even any two things. Even keeping it to three is actually a little bit tough. But in my view, and based on sort of what the literature says at this point, it's really three things. One is, one of the reasons we're seeing more wildfire losses in terms of structure losses and lives lost, economic damage, is because there are more people living in high-risk zones than there ever have been. So if the climate hadn't changed, if the forests hadn't changed, we would still be seeing more losses than we used to, simply because if you put more valuable things in places that can burn, they're going to burn more often if nothing else changes. But the problem is other things are also changing at the same time. And in a lot of forested regimes, particularly in the Western United States, we're left with a legacy of 20th century and even late 19th century land management and fire suppression policies, where we got rid of a lot of the beneficial natural fires that would have been on a lot of these landscapes. We suppressed a lot of the indigenous and cultural burning that was occurring for centuries to millennia in these places. And really what we did is we completely altered the conditions that these ecosystems had developed under for the past several thousand years in places like North America. And we did that over the course of about a century. All the while, the climate is warming. And this is the piece I'm going to focus on the rest of the talk today. But it is important to realize that, these three pillars are all important in different contexts. And in specific places, often one will dominate. And so your mileage may vary literally as a function of your miles. But the one that's overarching and that is relevant everywhere is climate change. So in some places, of course, if you're in the middle of a national forest, not too much urban expansion happening there. If you're in a grassland or a chaparral environment, not so much forest fire management policy going on in those settings. But climate change is unfolding under all of these. And so it's essentially acts as this risk multiplier on top of these other multifactorial changes that are occurring.
And I thought I would kind of share some anecdotal experiences and also then apply it to Marin County. 2015, I was assigned to a fire called the Rocky Fire in Lake County. Lake County burns a lot, has a very short return interval for fire. So the total suppression really wasn't an impact on the Rocky Fire. And there were quite a few homes within the Rocky Fire, but I wouldn't say that pillar was a problem. Most of the time, fires are driven by one of three things: wind, fuel, or terrain. We will have a wind-driven fire, a fuel-driven fire, or a terrain-driven fire. Most of the time in Lake County, they were terrain and wind. And that will give a fire a shape that's more oblong rather than round. The Rocky Fire was the roundest big fire I've ever been on because it was not driven by wind. It was not driven by terrain. It was driven by the fuel that was just so remarkably dry. The first day I was assigned to the fire, I was watching this one piece of area burn. And before the fuel can burn, it has to drive off all the moisture out of the fuel, and then it will burn. The less moisture it has to drive out of the fuel, the more intense it will burn. The energy I was seeing come out of this pocket of fuel burning was beyond what I'd seen before. And I'm like, what is going on here? Why is it burning so intensely? I don't understand this. Several days later, I was seeing the same impacts, that the fuel was just so dry. It was burning so explosively hotter than I've ever seen it burn in my years of experience. Move forward a couple of years ahead to the fire called the Detweiler Fire in Mariposa County. Again, a county that has a very frequent return interval of fire. And we use historical fires as where we think we can stop a current fire. And so there's a road called Bear Valley Road, and we're pulling up into the fire. They go, "Hey, Mark, the fire never jumps Bear Valley Road." I drove up Bear Valley Road and watched it go over Bear Valley Road. "Mark, it never jumps the river." "Mark, it never jumps 49. "Mark, it never jumps 162. Well, guess what? It jumped all four of them, and we ended up evacuating the entire town of Mariposa. And the way fires really burn in Mariposa is that when the wind is blowing hard, that's when the fire was uncontainable. And then the wind would die down in the evening, and we'd go get it. The difference was on this fire, the wind would die down in the evening, but the fuels were still so available to burn because they were so dry from the climate impacts. And I was standing at the Mariposa High School watching the fire burn into the town of Mariposa. I'm going, and that was when I literally said to myself, wow, this is climate change making an impact on this fire. Now put that into Marin, where we do have a legacy of 20th century fire control, where if you look at our fire return interval in the early 1900s, late 1800s, we're talking 8 to 15 years return interval for fires. Right now, we have a return interval of about 50 years. So you see the cleansing nature of fire has been completely altered here in Marin. And, you know, a lot of it was driven by the 1906 earthquake, the demand for lumber out of Mount Tam to be sent to San Francisco to build homes. And it was like, wait, we need to stop fires on Mount Tam so we can have lumber. And so when that fire suppression started happening in the the late teens and the early 1920s, that's when you see a dramatic change in Marin on a return interval of fire. And then you look at that expansion into the high-risk fire zones. And so Marin has dodged bullets on having devastating fires, but we have significant impacts of all three of those pillars.
Yes, and it really is, and I think this is something that's often missed, is it is the vegetation dryness changes that are the main, and I'll talk about this a little bit more in a minute, but that really is where the rubber meets the road in terms of the climate change impacts on wildfire. There are some other things too, but it's often, ironically, the one thing that is often neglected in studies of climate change and wildfire, or colloquial analyses saying like, oh, well, the winds aren't getting stronger. I'm like, yeah, we're not saying the winds are getting stronger. That would be a problem, but that's not the problem that we're seeing. It's the fuels, it's the vegetation, the character of the fires that you get with that drier vegetation is very, very different.
And like you said earlier, the overlap of our windy periods with the fuels being dry enough to be available to burn.
And in California, that is a particular issue where it's not just a question of how dry are the fuels, but it's also a question of, are they dry at peak dryness when it's also windy? And the answer is often no. So that doesn't happen every year. Something else I'll get to. I'll try and resume through a few of these just so I don't linger too long. But speaking of the 1906 earthquake, actually, just for perspective, is that we haven't had really deadly earthquakes in California recently. More people have now died in wildfires since 2017 than in all of the California earthquakes since 1906. It's the the era of mega fire in California, and hopefully I don't jinx anything with that statement. That's partly because we haven't had big earthquakes recently, but it is an indicator that this is something that if you lived in the first half of the 20th century, people generally didn't really, with some exceptions, there were some firefighters who died in initial attack, sort of these high risk situations while fighting the fire. But this wasn't something that came into towns and killed people generally in California in the early half of the 20th century, even though modern firefighting is way more advanced and sophisticated than it was 50 to 100 years ago. We're actually seeing more people dying in these wildfires today than we used to. That's striking. And by the way, this chart ends in 2021. If we had extended it a couple of years, we've had 2 very quiet years in terms of wildfire in California. So this is an older slide, but just for transparency, there are 2 years at the end of this that are a lot lower. The problem isn't so much what's happening in the ordinary years. The problem is what's happening in the extraordinary years. And you can kind of see that here, where it's really the low years are still really low, but the highest years, boy, have they just skyrocketed in terms of the changes we're seeing. And the reason for this, this is really aridification. This is the effect of rising temperatures and that vapor pressure deficit, the thirstier atmosphere that I'm talking about. This is irrelevant. It doesn't even matter what's happening with precipitation here. This is happening, even if precipitation were to increase, you would still be getting an increased vapor pressure deficit, an increasingly thirsty atmosphere. And this leads to, during droughts and the peak of the dry season, increased depletion of soil water. Plants draw water through their roots to the tissues to stay alive, to photosynthesize. If you get to the point where there's simply not enough water to do that, plants first, they'll become stressed. They'll go into modes where they shed leaves. This is why during extreme heat waves and severe droughts, even your mature trees may shed leaves. They may not be dead. They may recover the next time the water comes, but they're behaving differently. Their living tissues start to become drier. But this is even more pronounced with vegetation that is not necessarily alive, dead fuels, as they're called. Most of the seasonal grasses in California are dead by the time you reach peak dry season. So you have the brown grasses are behaving as dead fuels. Logs in the forest floor are heavy dead fuels that take some months or some weeks at least to respond to dry conditions. So if there's a damp log on the forest floor and it gets really hot for a few days, it'll still be damp. But if it stays hot and dry for weeks and then months, that log is going to start to dry out and become firewood, essentially. And so the thirstier the atmosphere, the greater this evaporative demand, the more intensively and the faster that occurs. And the easier it is to get to extremely dry levels than it used to be in a shorter amount of time. And there's already a lot of evidence that over half of the observed increases in the forest fire area, specifically forest fire area burned in the western U.S., which is most of the land that burns in the western U.S., can be directly attributed to this fuel drying effect alone. So even if you only isolate it to this one piece, it's actually a huge part of the picture. And this is just a quick overview of some research that we've done looking at extreme fire weather, taking into account directly the meteorology, how hot, dry, and windy is it from an atmospheric perspective, but also how dry are the fuels. So some people will do this analysis and not have a fuel moisture variable, and I say, what are you doing? Because that's the main thing that matters. But if you include it, and you're talking about, your personal experience since the mid-'80s, this is essentially that chart. This starts in 1980, a few years before, but it's incredibly dramatic. We've seen more than a doubling in the number of extreme fire weather conditions in California, something that is going to continue. We're going to continue to see this increase. Again, we've had a couple of quieter years at the end of this chart that aren't on here. But I think 2024 is going to be another rather high year on this chart at the upper end, well above the long-term average here again.
So I have another science question for you.
Yeah.
With the vapor pressure deficit, and then we've always had what we call our time lag for the fuels, 1 hour, 10 hour, 100 hour, and that's how fast moisture goes out of the dead fuels that are on the ground. Does the vapor pressure deficit actually change those time lags?
Yeah, that's actually a really good point that I haven't ever heard articulated before. It probably does. The question is if it's a significant amount. I think it could be an interesting science question, especially for heavier fuels. So we talk about the 6 hour fuels. This is essentially grass. It's stuff that if it's damp in the morning and it's incredibly hot, dry, and windy in the afternoon, your grass is going to dry out that day. 1,000-hour fuel, big log on the forest floor, that could take a few weeks to a few months. But is it, something that would have taken, so I think it's probably most relevant in the heavier fuels. if it's something that would have taken a month to dry out historically, is it now 3 weeks, or might it be 2 weeks in the future? And that's plausible, because we're talking about increases in evaporative demand that are on the order potentially of 20, 30, 40%.
Which I know that some of the fire behavior analysts that I've worked with, they've been frustrated because today's wildfire models have not been predicting fire spread in the same way that we have been observing. And so, I mean, something's not right.
I think this year is a good test of this. There are parts of Northern California that had above average precipitation this past winter. It wasn't a particularly, dry or hot spring, but it has been a particularly hot and dry summer starting in about mid-June. And we're seeing fine fuel moistures and energy release values, an aggregate measure of vegetation dryness, essentially, at or exceeding record levels for the calendar date now, following what was 2 wet years. How is that even possible? Well, this is essentially how it's possible. It's been record hot in the interior of California and extraordinarily dry over the past month or so. And so, this is I'm going to zoom through this, since I know we're running a little bit long, based on where I would like to be, since I want to have some time for questions. But essentially, what is becoming clear is that this specifically, this relationship between vegetation dryness, fuel aridity, even in the context of changes in precipitation that may not be doing much on average, is a key effect of climate change, and it is a nonlinear effect of climate change. This is something where each fraction of a degree of warming is probably going to bring about a larger change than the previous one. And that's a real challenge, and I think that's sort of why we're seeing people's gut feeling, people who are on the ground, the fuels people, the firefighters who are actually watching these fires jump over the roads, jump over the rivers. This is sort of where that is manifesting, where the anecdotes are lining up with the evidence, and it's qualitatively nonlinear. It turns out it's also quantitatively nonlinear. Funny how that sometimes works out. And I don't even have a slide on this because this paper just came out last week. And it's not a California focused paper, but it's looking at global fire severity. And essentially what it's saying is, outside of tropical grasslands, which is not where we live, fire intensity, not the number of fires, not the acreage of fires, that's also increasing, but there are various caveats with that. But if you only focus on how intense are the fires, in most ecosystems, they're becoming significantly more intense. That's no longer an anecdote. That's actually something that can be quantified, and literally now, as of last week, is quantified. It's real, it's there, and it's driven mainly by these fuel effects. And this is just a brief video. I don't know if you'll hear any audio, so I guess not. So it's a dull roar, essentially. But this is a giant fire vortex, a pyro vortex that I saw this is in Colorado a couple of years, I guess 2020. It feels like it's been more than a couple of years. But again, this is an October fire. It's usually snowing by this time of year in this part of the world, and yet instead, there was this large wildfire. At the time, it was one of the more destructive fires in the county history. It burned a few dozen homes, produced this really extreme exotic fire behavior. Vegetation was, again, at record dry levels. It was very windy. The winds were about 60 miles an hour when I was standing taking this. It is a windy time of year, but this is another part of the world where usually by the time you get to October, it's relatively cold. It snowed once or twice, and so the fuel moisture is not at peak seasonal dryness levels, but this year it was. It was over 100 degrees on Labor Day. It was really hot all the way up through mid-October. It was shorts weather when this occurred, when it was often be snowing, and then we got the winds. This was the result. And then just a few years later, again, this is a Colorado example. Oh, this is still the Calwood fire, sorry, but this is the other one. Less visually dramatic event, but actually far more destructive event. This was the most destructive wildfire in state history. This is me just turning the camera around the opposite direction, essentially 4 years later, or 2 years later. Again, all sense of time blurs together the last few years, but this was December. This fire happened a couple days before New Year's Eve, the middle of winter, and it was so dry that everything that this fire touched burned like crazy. Again, very windy day. So everyone said, oh, well, it's a wind-driven fire, so blame the wind. I'm like, yes, this disaster would not have unfolded but for the winds. But also, it wouldn't have looked like it did if the fuels hadn't been as dry. And again, the autumn of 2022 in this part of the world was the warmest and driest such period on record, beating out only October of 2020, where the previous fire occurred. So this is not coincidental. These are the dynamics we're seeing. It's true globally. I won't focus on this map too much, but the point is, this is a study projecting or not projecting, observing what are the observed fire weather trends globally over the past several decades. Do you see any blue on this map? There's a little splotch in the Himalayan mountains. Everywhere else, if there's any change, it's bright red. So there's some burning questions here, literally burning questions. What is the physical reality? Well, we see an increase both in precipitation intensity on the one hand, that's maybe a flood question for another day, but also in overall aridity. We can kind of cross off snowpack here. We don't have that in Marin County to begin with, but longer and more intense fire seasons. And can we mitigate some of these risks though? I mean, this all sounds bad and scary, but one of the problems is, not just climate related, but that we've modified these natural fire regimes well outside of what they would have been a couple centuries back. Can we sort of reimagine fire, beneficial fire? And how will ecosystems themselves change, not just as a result of fire, but as a result of other things that are changing, climate wise and otherwise? Will we see, ecosystems, especially in post-wildfire regimes, that forests that don't return as forests that become grasslands or become woodland environments? In some cases, this may actually be a beneficial change from a risk perspective and from an ecosystem perspective. But in other cases, it might just mean that we have invasive grasses that come in and allow the same areas to reburn essentially almost every year. There was at one point a question about whether we would see a negative feedback, so a self-diminishing process where we would see this initial spike in wildfires, they'd burn so much, and then the fuel would start to go away, and then we'd actually see things level off even as the climate continued. Unfortunately, there's now evidence that that's not how it works in most settings, because we do see these type changes. We do see transitions from forested ecosystems to scrubland or to brushy ecosystems or grasslands. But all of that is actually still pretty flammable. So we no longer get forest fires there, but we get brush and grass fires, which can still be very intense, particularly in a warming climate. And they can happen more often because a forest takes decades to regrow. Grass can be there again the next year, certainly within a year or two. So that brings up new questions as well. And I just want to check in on the time that we have since, how are we doing? What are we budgeted for? How long are we going for?
I think maybe 5 minutes or 10 minutes, about 5 minutes more talking, and then we'll have questions.
Okay, so I'm gonna go through this quickly. The short version of this research that we just did, that published last year, is that it does look like climate change will reduce the windows for prescribed fire, but we're so underutilizing the ones that exist that even if those windows decrease by half, we could still scale it up dramatically from what we're currently doing. That's the very short version, but it might require winter burning, which in a lot of settings, we're not always equipped to do. All right, so to get to some of the Marin County specific insights, everyone here is pretty familiar with Marin County, so I won't spend too much time on that. There's a lot of WUI, the wildland-urban interface. There's a lot of structures intermingled with the vegetation, a lot of narrow, windy roads with limited access, limited ingress and egress. Nearly all ignitions, the fires that do occur in Marin County these days, they're almost all human caused because really the only natural cause is lightning, and that does not happen very much, particularly in the warm season when vegetation is dry enough to be receptive. It does occasionally. We did see that in 2020, but we've gotten lucky with those lightning fires in recent years. And then a lot of the fires that we do see, they're mainly like roadside grass fires or smaller brush fires. That is the recent fire history with a couple of exceptions in Marin County. We don't have, fortunately, the recent history with destructive, catastrophic, whole neighborhoods burning type fires that many other places in California, including places, only 10, 15 miles away, have experienced over the past 30 years. That's a blessing so far, but also, does it mean that we sort of have we've sort of limited our expectations based on what we've seen recently in a way that might not be fully adaptive to what's to come? I think this is especially interesting in the context of, and this is a little bit of a supposition or a hypothesis, but I think it's partly supported by the fact we haven't seen many years with large fires in Marin specifically, is that the risk here is a little more conditional and episodic. The very worst plausible risks are super high. we don't experience them very often. There are certain places in Southern California that have extremely high fire risk, like 70 days a year. That's not true in Marin County. In fact, I think there's some years where we never really get extreme risk days. Some years where we get one or two, maybe some drought years where there's more like a week or two of it, but it's not especially common, although it does occur. Uh, and that's partly because, as we've been talking about, you really need this overlap between extremely dry vegetation and some other trigger, either strong winds or exceptionally dry fuels to the point where you can get fuel-driven fires, where the dryness, the aridity of the landscape itself is the sustaining force. And that doesn't happen all the time in Marin, although occasionally you will see those combinations. And as I mentioned, we don't even see those every year. The really extreme iterations don't even necessarily happen every decade, although they are likely increasing in a warming climate. So sometimes it can be really hard to prepare for things that are unseen. We don't experience them very often, out of sight, out of mind. You kind of have to be a little bit imaginative in thinking about where the risks are and what they will look like on the bad days, because we don't see those bad days as often around here as you do in other parts of California. Even up in Sonoma and Napa counties or the East Bay Hills, we see these conditions more often than we do in Marin, even though the ceiling on that risk is probably just as high here as it is there. And maybe this is a topic for another conversation, but the other wild card here, and I was thinking about this driving through Central Marin yesterday, is sort of the post-earthquake fire hazard is not entirely divorced from the climate change hazard here. Not because climate change is increasing the risk of earthquakes, there's no evidence of that, but just because we know we're a seismically active region, we know we have certain times of year when the risk of wildfires is seasonally high. If we do get a big earthquake in the fall when it's dry, that's the big risk is going to be fire in the Bay Area in general, and in particular in Marin County, because that's that other trigger. I didn't mention it above. It's exceptionally windy, exceptionally dry, or if it's exceptionally difficult to get firefighting resources to fires when they start. And that would be the case during a major earthquake event, because of course you've got a lot of other things to do and you might not have full access. So just another piece and sort of thinking creatively about plausible worst case, not just to scare people, but really to think about the kinds of risks we can prepare for, what the plausible scenarios are that would be our bad days, and then how to sort of outthink them and prepare for them in advance, because the whole point really is to avert some of those potential future losses that could occur otherwise. And so not everything can be prevented, but I think a lot of it can, and just to end this, since I know we're running long, I'll skip the last couple of slides, but to end it on a positive note, I mean, driving through Marin yesterday, I was down on the peninsula and drove north. I got off of 101 early because there was a lot of traffic and said, oh, I'll take the back roads through the hills. And, driving through Mill Valley in Central Marin, the roadsides look a lot different than they did when I was growing up in Marin County. And I really, there's been a lot of vegetation management. I mean, the roads, I think they're functioning more clearly as fire breaks. There's not very much grass along the immediate road margins. These sound like small things, and they might not be enough on a really bad day, but they're pretty significant changes. And so it's very obvious that there's been some real attention paid to this in the last 5 or 10 years. Perhaps because of the hard lessons learned elsewhere in California during this period. And, I'm hopeful that hopefully Marin County will be a place that gets to benefit from the lessons learned without having to experience that kind of event here locally. So I'm just going to end it there and just put you on my last slide so you can see my contact info if you're interested. So we have some time for discussion.
And we were talking about the prescribed fire piece, and we are slowly reintroducing prescribed fire in Marin. And part of it is getting the residents used to seeing good smoke, as we call it, up in the air and not being afraid of that good smoke. But we do have to start small. And we also have to do some point of entry work or first entry work, because the fuel conditions are such that if we try to do prescribed fire in some areas, we are not going to control it. And that's the last thing we want to do, is start a prescribed fire that we can't control. So a lot of our vegetation management work we are doing now is designed to perform the same type of function that low intensity fires did before we stopped allowing low intensity fires. And then once we start getting the fuel conditions to a point where we know that we will be able to have healthy and beneficial prescribed fire, that's when we can start scaling up. But I did want to introduce Ann Krelock, the Planning and Program Manager for Marin Wildfire. She's going to help facilitate the questions for us. And if you know anything about Marin Wildfire, you know there's the brains right there.
No, I disagree wholeheartedly. Yeah, Ann Krelock, Planning and Program Manager with Marin Wildfire. And, you know, the vegetation management piece is a really key, it's one piece of what we do, but it's a really important piece of what we do. So for those who are not familiar, we work in the home hardening and defensible space world, in evacuation planning, alerts and evacuations, public education with many of our partners, some of whom are here, Fire Safe Marin, for example, as well as vegetation management. And we really feel that with the vegetation management, there's a huge ecological component of that also. And so, you know, one addition I would say in terms of the vegetation, the condition of the vegetation is the change in vegetation with invasives from other parts of the world that have really invaded a lot of our ecosystems. In many of our projects, what we're doing is removing non-native invasive plants that are dominating the understory. We've got broom species from various other parts of the world that really dominate the understory and can serve as major fuel for a fire. So one of the questions we've received from others, and if you have questions, please feel free to pass them up on 3x5 cards. If you've already used your cards, please feel free to grab another one. We only have a few questions currently. Mark and I are going to ask them. I'm going to ask this question from online, and it has to do with vegetation management. And the question is really about timing and how climate change might change how we manage vegetation and the timing for when it's appropriate to manage vegetation. This person specifically is working on this issue with their HOA and is wondering about how climate change might change their practices managing vegetation and invasive species.
Yeah, that's a good question. And unfortunately, I skipped through that slide on prescribed fire and climate change a little bit quickly. But I think for coastal Northern California, so Marin County, essentially, the piece that, that matters there is that it does look like, we're seeing longer fire seasons. But there is, in terms of vegetation management, there's prescribed fire. That's one way to manage vegetation. Sometimes you have to do, as you mentioned, the initial entry work to get it, the vegetation into a state where you can safely do those prescribed fire treatments. And I think that the weather and climate constraints on that are greater for prescribed fire because you're intentionally introducing fire into that setting. The other vegetation management regime, hopefully you're not resulting in too many sparks on the landscape unintentionally when you don't want them. So the main constraint would probably be from a prescribed fire perspective. We know that it's not a good idea to go, use heavy equipment in the grass and brush when it's hot, dry, and windy. And even this past week, a number of the significant wildfires that have occurred started because people were doing vegetation management at the peak of a record-breaking heat wave. Probably not the best idea, but people are clearly still doing it, so perhaps that message has not gotten out. But from a prescribed fire setting, I think the challenge and the opportunity will be longer fire seasons. But just because it's fire season doesn't mean you can't do prescribed burning. You need to be looking at the specific conditions that are actually in place the day you're doing the fire. Ultimately, that's what matters. And it's likely there are going to be long windows in spring most years. They may be earlier in spring, so maybe this is more of a March-April thing and a drier year versus a May-June thing. But there are always going to be these windows, depending on how things are going, where you're able to do prescribed fire safely in different settings. And there may be some windows emerging in winter, in dry years in particular. It may be that in a dry year, the middle of winter is the only time of year where it's safe. It's essentially safe, where it's not extremely dry and hot to do some of these prescribed treatments. This is in the West-wide context, this is a challenge because entities like the Forest Service, for example, they don't have, in most cases, a year-round fire crews. These are seasonal wildland fire workers who are tasked with fire suppression specifically. There isn't really a large contingent of people who have the time or the availability to do these prescribed fire treatments in winter. Marin County is maybe in a little bit more of an advantageous situation there because there's not as much seasonal hiring, as far as I'm aware, for fire crews. So it may be that folks who would otherwise respond to wildfires at the peak of fire season can be more directly repurposed for prescribed burning in a place like Marin County because there is more local and county level resources available to do that. That's one way of thinking about this from a vegetation management climate perspective.
One of the questions that we have from the audience here is, and you mentioned a recent paper that talked about the intensity of wildfires. How do you quantify the intensity?
Well, that's a good question. The way that these recent studies have done so, to be succinct, is essentially looking down from Earth orbiting satellites and saying, literally, what is the radiative power of these fires? What is this size times thermal intensity? So literally, what if you multiply the area of the fire by the temperature at which it's burning as visible from space? So obviously, we're talking about fires that reach a certain level of intensity to be counted in this way. That is increasing. So it's sort of the aggregate of size and literally temperature. Now, of course, the temperature matters not just directly, but as you and anyone who's worked on a fire line well knows, it's not just that hotter fires are hotter in some way, and that just makes it incrementally more intense, but there's this nonlinear effect where at a certain point, a low intensity fire really is something, a really low intensity grass fire, something that's smoldering to the underbrush is something you could walk over in jeans with your pickaxe, but a extremely intense fire is something that no amount of water could possibly extinguish. You might have flames a couple 100 feet tall and burning at thousands of degrees, but it produces these exotic fire effects. We see these tornado-like events within wildfires. We see these fires that generate their own thunderstorms. This happened in 2020 like 30 or 40 times on California wildfires, where the fires got so intense, they developed their own tornado-like vortices and started producing lightning. So you can see how there's this feedback where it's not just fires are hotter, they move incrementally faster, but they start becoming completely different hazards and entities. Fortunately, we've not seen that level of fire behavior in Marin in modern history, but the point being that the intensity matters because not just of the incremental increase in the temperature of the fire, but because of all these other phenomena that increased intensity can engender when we're talking about large, very hot fires burning in areas with complex topography and under extreme fire weather conditions.
And here's a question that we see a lot, and a lot of it I think has to do with the public's increased attention to wind. And the question is, and I think you touched on it a little bit already, but are wind patterns changing with climate change?
Yeah, and we get this a lot because the winds are really consequential. And the answer is there's not much evidence that they are, which doesn't mean that they aren't or can't or won't.
You like that, meteorologist? 50% chance of increase of rain.
Right. I mean, yes. But, I have made a lot of pretty bold statements otherwise. And here I'm just kind of saying, we don't really know. And there's not a strong theoretical reason to think that it necessarily should. But I think that the interesting thing here is that the relationship between wind and fire is likely to change even if the winds themselves don't. For precisely the region that you mentioned, if we have greater overlap between peak vegetation dryness and drier peak vegetation dryness than we used to, and we have exactly the same historical repeating pattern of autumn winds as we used to, that alone is going to result in this nonlinear effect on fire activity in California because we're more likely to experience a historically precedented wind event under historically unprecedented fuel conditions. We've had offshore wind events in the Bay Area, 60, 70 mile-an-hour winds in the past, but it had rained a week before, and there's really no meaningful fire activity. There's a couple of grass fires that start, and they essentially self-extinguish before the fire department gets there. That won't happen if you're at peak seasonal vegetation dryness during an autumn wind event, and that is why that's so important. Those are preferentially the most dangerous fires in coastal California because they're occurring at peak seasonal dryness if the rain haven't arrived yet, and because they're being pushed by winds that can cause these fires to do things they wouldn't normally do under more ordinary conditions.
Great. If I have time for two last questions, I'll ask two. And if I have time for one, then I'll choose this one. Two questions or one? Two?
I'll try and be a little more succinct.
Oh, no, it's great. So assuming two questions. In terms of air quality standards, I'm going to paraphrase here, air quality standards and working with our air districts, there are, two arenas that we're working in. One is wildfire related health impacts and the other is in the prescribed fire world. Do you have any thoughts on that and how to improve kind of the science and support for in the air quality world?
Yeah, and this is a big one. So air quality management, just to be really quick about it, is a patchwork. There's regional air quality monitoring districts. Some places aren't any, and then there's sort of very high level top-down EPA rules. But generally speaking, there is no single regulatory framework for air quality as it relates to prescribed fire. So prescribed fire, of course, is going to produce some amount of smoke. It's usually going to produce a whole heck of a lot less smoke than an uncontrolled wildfire burning in the same place, because you are not getting, in most cases, the same intensity, which affects, the intensity of combustion affects both the amount and the chemical compounds that are in the smoke, and also the completeness of vegetation combustion. How much of the available biomass do you actually burn is going to vary as a function of fire intensity, which you can more intentionally and purposefully modulate in a prescribed fire setting than you can in an uncontrolled wildfire. And so you're going to get smoke either way. But the reality is there's going to be more smoke on the horizon or in the air that you're breathing in a warming climate than there used to be. So the question is, do we get more of it in these uncontrolled wildfire episodes that result in these enormous, extremely dense, extremely intense, potentially public health emergency level air pollution episodes? Or instead, do we choose when we do these, when we have these fires, they're for shorter durations, there's less smoke emissions, and you can choose to do them on days when the ventilation is better. Sometimes wildfires occur, and this is what happened in 2020 with the Blade Runner skies in San Francisco. That smoke just got trapped and in a subsiding air mass, and it just started sitting near the surface. You would not want to do prescribed fires on days like that, and so you would not, and you can deliberately avoid it if you're choosing which days the smoke emissions are occurring on. So there's the additional element that climate change is probably increasing rates of air stagnation. So there's going to be even more days to dodge, if you will, on days you don't want to do prescribed fire, not just because it's hot, dry, and windy, but perhaps because it's not hot, dry, or windy at all, and the air is just stagnant. You might not want to do prescribed fires on those days either, is because all of that smoke is going to get trapped. My point is, that's all predictable. We have pretty good weather forecasts. You can choose. That can be a triggering for a go or not go. The challenge is, who are the regulators? What is the public perception of smoke? I think some folks in Northern California legitimately and understandably have actual PTSD from wildfires in recent years. And then there are other folks who are just generally worried when they see a smoke plume on the horizon. So part of it's an public education process, but part of it is having a frank conversation with regulators, which is that, yes, we're deliberately causing smoke, but we're deliberately causing smoke to then have less smoke occur later, which is there's not a good analog for that in other air pollution regulation realms. It's not like a factory can say, we're going to burn a lot today, so in the long run we burn less. That's usually not what happens. But that might actually be what happens in the case of prescribed burning and air quality. And also, just ended on a note, there's some evidence that the actual smoke produced by prescribed fires is physiologically less hazardous than smoke from intense wildfires. And that is probably because, hopefully in a prescribed fire, you're only burning vegetation. Wildfires that start burning structures and vehicles and commercial buildings are burning, hydrocarbons and toxic materials. But also, the temperature of the fire matters. Even if you're just burning brush and grass, the chemical species in the smoke vary based on how intense the fire is. So all of these are good reasons to really have in-depth conversation with local air quality boards and regulators. Sorry, that was not a succinct answer either.
That was a great answer. Thank you so much. Last question that I think I have time for here is, a little bit about the Marin Wildfire Prevention Authority and how we're trying to incorporate climate change and modeling and carbon and biomass into what we do. But the question is here, given the changing climate, given the urgency of it, given opportunities really for us to think about biomass and carbon sequestration and trees, do you have any thoughts about policies, projects, programs that are relevant for Marin County, or more specifically Marin Wildfire Prevention Authority, that we can incorporate into our practices?
From the conversation we're having today, I think it sounds like you're already doing a lot. I think thinking about scenarios is maybe something that I've been encouraging folks on the water and the flood side to do this, and we're working with the Department of Water Resources and other agencies and folks to sort of rethink, what are we afraid of? And also, what are the tools we have at our disposal to sort of allay those fears to a certain degree? And what happens when conditions are beyond what we're going to be capable of fully managing? I mean, under a sufficiently dire scenario, there's only so much you can do, but also under lesser scenarios, there's actually a lot you can do. And so thinking about those almost as separate questions, thinking about what are the ordinary risks that we can mitigate, it's very clear there's already been a lot of work going towards that. And then what are the extraordinary risks, and to what extent to what we want to do to avert and to mitigate those risks, are they the same or different from what we would need to do to mitigate the more typical types of things that we're worried about in terms of whether it's wildfire risk or something else. And so thinking about what those scenarios look like, what the adaptations or interventions might look like, and to what extent they're the same or different, I think is one piece that I'm really strongly encouraging all entities that are managing any sort of natural hazard or natural hazard adjacent risk to think about. And I think it's especially true in a place like Marin, where the day-to-day risks are actually not super high. Today, I'm relatively confident, again, I don't want to jinx anything, but the conditions today are not in place for a massive wind-driven fire in Marin County. We just don't have that weather today. There's some nice fog out there by the coast. It's not windy. But there will be days where that risk exists. And how does adapting to more of those days look? And to what extent, can we implement prescribed fire in the windows that we have? Because there may be fewer of them, but we're still going to have windows every year to do this. And so how can we flexibly make that happen?
And we are up against our time, but I don't see a lot of you guys checking your watches, but we also need to be respectful of Daniel's time. But I think Bill may have a question.
Yeah, I have a question. It's not in writing, but you are maybe one of the leading climate scientists anywhere who deals with this whole question of the attribution of climate change to extreme weather. And many of us who work in this area are dealing with this issue, how to relate what's happening with one of the massive fires or smaller fires to climate change. And I just wondered if you wanted to say whether you thought that situation was getting better, whether you thought that some meteorologists are actually learning more about it and informing the public better, maybe. So I just wonder what you thought of that situation.
Yeah, thanks for that. I mean, I think that this notion of extreme event attribution in a climate change context is essentially saying that, okay, there's this extreme heat wave, there's this severe wildfire or a big flood somewhere. To what extent did climate change play a role in making this event more likely to occur in the first place, or worse than it would have been otherwise? Different dimensions to that, but essentially asking that question quantitatively, and I think that it is this emerging field, and frankly, there are still some climate scientists who are even very reluctant to make that leap, and I don't really understand why, because all the evidence is there, the tools are there, the evidence is really clear. It can be difficult in the moment to say climate change made this particular fire X times larger, or Y times more intense, or this heat wave, Z degrees hotter. But if you ask me today, this current Western U.S. heat wave, I know in Marin today it's not bad at all, but it has been hot, and in interior parts of California in the West. I mean, Las Vegas, I think, has experienced its hottest days on record consecutively in the last 4 days in a row. Is this heat wave worse than it would have been without climate change? The answer is obviously yes. And we can give you some general idea of how much worse without doing a formal study on it. And with a formal study, you can maybe get a little bit closer to the exact number. But I think this is conspicuously absent still in a lot of our conversations. If you see a lot of the news stories about this ongoing, literally this event that's still unfolding in different parts of the West as we speak, the fraction of news media articles that talk about the role of climate change, it's a minority of articles still in this year 2024. Even a significant minority. In a national context, recent studies suggest it's something like 1 in 5 stories about record-shattering heat talk about climate change. How is that true? It boggles my mind. I guess what I'm getting at is we do need to be having these conversations, and we can have them in quantitative and scientifically supported ways. And I don't think we can reflexively blame everything on climate change, on the other hand, but climate change does have its, its finger on the scale here when it comes to wildfires. Would every wildfire disaster not have been a disaster without climate change? No. I mean, we've seen wildfire disasters before. Does every wildfire event have the same contribution by climate change? No. There are some events that are more clearly influenced than others. But overall, there's just such overwhelming evidence that that effect is there, that when we have these individual events, I think it's almost becoming malpractice not to talk about the influence of climate change. It's almost a conspicuous omission, I think. So yes, I think that there has been progress, certainly scientifically, to a limited extent in the public conversation, and yet I'm actually surprised that we aren't talking about it even more than we are today.
Thanks.
Well, thank you, Daniel. And I know we could all just like burn up the rest of your day. And Daniel does have a place that he needs to go after this. So out of respect for our time, I want to thank Belle for being a real spearhead and her drive to put this forum together and getting Daniel to come and participate with us. Daniel, thank you very much. An incredibly interesting conversation. Thank you all for coming, whether you were virtual or in person. I know that we didn't hit all of the questions, and reviewing some of the questions looked like they may have been written before some of the slides were hit. But what we can do is that we can collate the questions and provide answers. I'll work with Daniel offline, and then when we post a video on our YouTube page, we'll also include a link to the Q&A so that that way you all get your questions answered. So again, thank you very much.
Thanks again for having me. So it's actually, this is technically the first scientific talk I've given in San Rafael in my life. So there you go. After all the talks. Thank you. Appreciate it.
What? Question? Yeah, the whole thing.
Yeah, it sounds good. No, I'm happy to go through and we can talk about everything.
I'm just wondering, has somebody come in here and thrown dimes around? They're about 7 or 8 or 9.
Weird. Hi, Jen. I was thinking for you that I don't know why I didn't think about this yesterday. Yes. Fair, and they're set up with better bars. Yeah. I was going to buy mine at hospital. Yeah, the hospital has.